right. Hey, everyone. I'm Rob May. I'm the CEO of Neurometric.
And I'm Cooper, COO at Neurometric. We're co-founders, and this is Inference-Time Tactics, a podcast for builders, researchers, and engineers who want to understand what's happening in this next wave of AI.
So today we're joined by Yash Sharma, an AI researcher who just defended his PhD from the Max Planck Institute, where his work has challenged some fundamental assumptions about how AI models generalize. Yash's research spans a topic called compositional generalization, adversarial robustness, and what it actually means to say a model can do zero-shot learning. He spent time at Google Brain and Meta AI, and so we're going to talk today about what some of these topics actually mean in plain English. So Yash, before we dive in, do you want to give our listeners a bit more context about your background and how it connects to generalization and some of the inference-time compute stuff we're going to talk about today?
Absolutely. So my name is Yash. I've been an AI researcher since 2017. I worked on adversarial examples from 2017 to 2019, started my PhD then worked on theoretical solutions for generalization. How do we design models that'll generalize out of distribution? Happy to discuss more about what that means. And then more later, looked at sort of foundation models, LLMs, text-image models, and how can we kind of control the data that we feed into these models to improve their ability to generalize. And I think inference-time compute is definitely very interesting. I think there's definitely some very interesting implications that haven't really been explored very well in terms of how generalization affects inference-time performance. And I'm happy to dive further into that on this podcast.
Absolutely. That might be a good starting point, like understanding when and why models fail to generalize and how this might constrain what's achievable.
I would say models do generalize to some extent. And so if we look at just the latest and greatest in models like GPT, for example, I remember, I think Peter Lee at Microsoft, he had a nice example where he would go up to a room of people that don't know anything about AI and try to push as to why GPT is amazing and why it's not just a memorization machine, for example. And he pulled the audience and he asked them, pick a topic, any topic. And so one person said Charlotte's Web, for example, and another person said some very small, very niche, I think, volunteering organization. And then he types into GPT, write me an essay that discusses the intersection of Charlotte's Web and this community startup organization. Something that there isn't any essay written on that if you were to look it up on Google search. And then GPT output an essay. And of course, this you could say is very subjective. In terms of essay writing, that an essay that's worded well and kind of just vaguely discusses the topics, maybe ends with a nice heartfelt note, seems like a good essay. But it was to indicate that there wasn't any document on Google search. It didn't just regurgitate the essay. This prompt likely didn't have a correct answer in the training database, but it still outputted something reasonably well. So I would say it's a misnomer to say that models fail to generalize completely. And I think a lot of people on, say, the AI critic side sometimes speak in a way where that kind of implies what they're saying, that these sorts of foundation models will never amount to AGI because they fail to generalize. But we need to be more specific about what we mean. I would say the state of research today is that these models generalize, but generalize unpredictably. So as soon as we move away from the training distribution, they might work well, for writing some essay where it's kind of fine to write about anything. But what we don't see is scientific discovery, for example. We don't see novel ideas. There's recent benchmarks like AlgoTune, for example, where they're asking models, this is kind of based on the SWE-bench sort of work, where they're asking models not just to fix software issues, but to optimize code. So to take, for example, some implementation in some scientific computing libraries and make it more efficient. And you can see that models perform quite poorly on this task. And even the authors of these kinds of papers, when they look at the solutions, they're look, they didn't really come up with anything new. They didn't come up with a novel algorithm that is more efficient. They instead might have refactored the code in this way or that way. It's very interesting to generalization really simply means you're exposing the model to something it hasn't seen in training. And in that way, you can say that models do generalize. But you can also see very clear limitations to these models in terms of scientific domains, novelty, etc. And so the way our work kind of poses the problem is, can we at least predict the scenarios where the models do generalize and be able to kind of separate from what is easy for models today in terms of generalization and what is hard? And what we found is that these models successfully generalize compositionally. So what that means is that you're taking a test prompt where the model has seen aspects of it. So if we take the example of, say, writing an essay about Charlotte's Web and this community organization, writing an essay, it's seen documents that wrote essays before. Charlotte's Web, there's plenty of essays about Charlotte's Web. And then maybe this person's organization is the hard part, but if it has tools, they can maybe Google search and find information about that person's organization. And so it has information on each of these pieces. It's just never put them together, which I would argue is almost always like the real world generalization we see in practice, where we're not coming up with entirely new terms. We're just putting existing things together in new ways. There's some arguments that that's kind of the bedrock of creativity, novel compositions of things that exist. And we kind of iterate in science in that way. When we look at compositional generalization, what we find is that we can easily predict when models will succeed or fail based upon either the diversity in terms of the concepts and combinations in the training data, or even as simple as how many examples the model has seen in terms of these individual concepts. And so, for example, in that Charlotte's Web example, the reason why we might expect that the model will fail here and maybe reduce the probability of success would be that community organization is likely very underrepresented in the data. If we really want to build AGI, for example, we probably want models that are good at searching for information that isn't really in their databases and kind of prevent that. And so, in short, when we look at pre-training these kinds of models, you can very easily predict their ability to generalize by looking at how represented the test prompt is in the training data. But when it's not very well represented, without any additional tooling, these models don't perform very well.
And so you mentioned kind of it's challenging, but we can measure this. And so how do you benchmark it? Like, how do you take that research and make it more actionable for builders and people thinking about this space?
I would say generalization is a very broad topic. You could say that even back in 2012, when AlexNet happened, which kind of really drove this deep learning revolution, it's not like they were measuring memorization performance. They were measuring what was called IID, generalization. And that's just a fancy statistical term for we collected a bunch of data and then we just randomly split it into training set and test set, which would mean that whatever data we trained on, say are images from Instagram, and then whatever we're testing on is also images from Instagram, just a different sample of images. So if the model, from a statistical sense, has fit the distribution of images from Instagram, it should perform well even on samples as seen in terms of images from Instagram. The model's deep learning performed really well in that case 10 years ago. So you could also argue that that's generalization. So then we moved from IID generalization to OOD generalization. So imagine, say, a self-driving car. It trains in daylight, for example, and then now you benchmark in a nighttime images. So this is not the same distribution. You could sample infinite images from daylight images in the real world, but you'll never get a nighttime image because you constrained the distribution in that way. And then you see that models fail. So models succeed at IID generalization, they fail at OOD generalization. Then you look at, say, adversarial robustness. Adversarial robustness was an instance of, can we just find the smallest change we can make to data that models do perform well on, where they now catastrophically fail on? And then you end up with scenarios where you have images or sentences, etc., where the examples look almost the same. So for example, you have a panda image, it's still a panda image, but now you can get the model to output gibberish on the panda image, for example. So this is, again, OOD generalization because the pixel modifications you made didn't happen in practice. It's not like any camera picked up on the scene and had RGB pixels like this adversarial example. It was completely artificial. And so now you're asking for OOD generalization to an adversarial distribution where the models fail. The thing about compositional generalization is that it was traditionally studied in very restricted settings, so very academic settings. It's, I think, a term that was coined back in 1980s by cognitive scientists when, again, there was lots of debates about AI and whether AI could do what humans do. And I think they were using it as an argument for humans do compositional generalization all the time. And they were using very high level examples, like maybe we cook in one kitchen, for example, and then we go into a new kitchen, we're still able to cook. And again, this definition is so flexible, you can map it onto that situation. That new kitchen has all of these features, which are similar to your existing kitchen or your kitchen, but maybe it has a knife in a different corner. But you've also seen knives before, even different sort of knives. So you could take almost every novel situation and say it's a combination of things that you've seen before. And taking that definition, so I think they were arguing at that time that these are things that deep neural networks are poor at. And you can also argue that's OOD generalization, those failure cases before, because you could sample from your kitchen data all as much as you want. You'll never get that new kitchen, right? It's constrained. But in terms of the academic work on compositional generalization, it was coming up with toy settings. For example, let's take let's invent a new language, a very simple language, not like natural language. And let's create training data and test data. Let's constrain it. You could say actually my work on VQA is similar in this way, where it's a simulated world. You're creating a synthetic world where you can really control that the model has seen this, but hasn't seen that. And then you're benchmarking generalization. The limitations is that I think people, especially practitioners in AI, definitely know that you could investigate toy settings all you want, but what we care about are real world performance. And if you have methods that work in toy settings, we immediately start to question, like, is this even applicable in real world settings? So the novelty in some of the papers we produced in 2024 was, I think, surprisingly, you could argue the first real world evaluation of compositional generalization, because almost all of that work in that space was in academia. And we just took the desiderata of compositional generalization, which just means on-scene combination of scene concepts. And we just said, as a way of measuring this, you can just take your real world eval that you care about and just take the test example, extract out what are all the relevant pieces of information, which is very simpler in terms of text. You could take text to image models and say a dog playing with the ball in the park, and just say that dog, ball, park, like these are things that the model needs to know in order to be able to answer that question. So you could do it in very ad hoc ways of just basically labeling, like what are all the things the model needs to know in order to execute this task. And then just see like, okay, based upon the training data, which again makes it difficult with closed models, but you can approximate it. There's some works which looked at, since we know these closed models are pre-trained on the internet, there's also a proxy in that way. Like, is this combination, like as we said with Charlotte's Web, et cetera, right. If you Google search for it, is it represented? And then for the individual concepts, are they represented? And so then all you have to do is take your real world evaluation, like let's say at the 1,000 examples, and just filter it based upon that. Which of these real world examples are represented in the training set and which of them aren't? And then if you want to be really particular about compositional generalization, which is actually important to make it a doable problem, you don't just keep the examples which aren't present in the training set, but you also say, I only really care about generalization on the examples where like the individual concepts that I labeled are present. Because if you take that to a human, for example, I think there's lots of arguments about this when thinking about human versus AI. If you say that the AI failed on, say, generating image of me, for example, a human would probably also fail at that if a human has never seen an image of me. And so you immediately get into, if you go beyond the definition of compositional generalization, you enter the world of extrapolation, where I need to somehow know what is the image of me or of you, even though I've never seen an image of that, which just is magic at that point. But maybe we hope that the models have seen images of me, you, etc., but haven't seen me robbing a bank, for example, but they've seen robbing a bank before. So this seems like something a human could be able to do. They know robbing a bank. They know about me. So they could probably draw a picture of me robbing a bank because they understand the concepts reasonably well. They already have the knowledge because they have the knowledge of robbing a bank, knowledge of me. They just need to put that understanding together to produce the example.
Right.
And so,
and we have so much opportunity now. We're moving towards a multi-model and systems orchestration world, right? So while the efficacy depends on whether the model themselves in this scenario are capable of eventually solving a task, we can introduce new small language models or specialized models. And how do you think about that in your work?
And can I tack onto that question as you're working through this? Some of these models, like, does the work apply to CNNs and RNNs and state space models and all this other stuff you're doing? So kind of as you're answering this, can you talk about how much of what you've found is LLM centric and how much of it isn't?
Of course, like when you look at research, right, you can test in God knows how many different scenarios. But then you kind of look at like, what is the principle behind the research and like how it's generally applicable? And so I would say our research is just specific to machine learning, which is very broad in that way. So what is the definition of machine learning? We're fitting models to data. And then what did we find in terms of how to predict generalization? You can predict generalization based upon the training data itself. And so if we think about CNNs, ResNets, transformers, these are different architectures, and we can talk a little bit about like why transformers like really won the day. But at the end of the day, they're neural network architectures, which are parameters, and we've learned those parameters or fit those parameters via optimization procedures to particular data. And when we think about multi-model setups, each of those models are also machine learning models. And so I think when you get down to it, the only aspect of AI that our research doesn't apply to are ways of going about AI that isn't machine learning, which is like symbolic AI, which is like rule-based AI. And it's actually I'm happy to talk about that further because it's very interesting sort of like these symbolic AI methods don't have this problem, but they have limitations in their own ways. And for example, Gary Marcus, who's very much a critic of LLM progress, et cetera, and saying that like we're making progress, but we're not making real progress. He comes from the symbolic AI camp. And symbolic AI definitely predated like the deep learning revolution. And so why is that? Why do I say that like it's specific to machine learning? Because it rests on something very simple: train test similarity. When anyone who's really worked with machine learning would probably be able to tell you, any practitioner, that when you train a model on some training data, the model seems to perform quite well on test data, which is like the data that the model has seen. And it performs quite poorly when you present it in a completely new situation. And it's very intuitive. If you train a model on like New York City scenarios, it's never seen a desert before. And then your entire test set is just desert images. It's magic. If like the model performs well there, you'd expect it to produce chance level performance. Like it's just randomly guessing at that point because it does not have the knowledge, essentially. When I think about ResNets, transformers, we actually looked at ResNets and transformers in our papers. We have plots which span training sets, test sets, different tasks, text image models, but also looking at, for example, a vision transformer or a ResNet. And then we find that the predictability, the correlation is there for both of these models. Their slopes, like the scaling law might be shaped a bit differently. Whether you use a ResNet, a vision transformer, the model will perform poorly on data it hasn't seen before. Like you're not getting around that with any of these architectures. So when we think about multi-model setups, I would basically just think about what are we asking each of those individual models to do? Like what is the individual model's task? And then what was that model trained on? Or how was that model trained? And then you could get an estimate. You could do this in a quantitative way or even just a very heuristic way of how confident are you that this system will perform. And that's, I think, the connection I would make between the very academic concept of generalization and the outstanding problems of today. We care, if we want agents to do software engineering work, we care about reliability. If we want them to do software engineering work, we also want them to be able to do new things. If you're not doing something new, then how are you creating value or creating ROI if you can only do things that you've seen before? When we want them to do scientific discovery, of course, like want them to train on what exists and do something new. And what this work basically tells you is that there are very simple ways of just getting confidence estimates or uncertainty estimates on, do you expect that your agent will be able to do this task? And it also gives direction for agent builders. If you can just take like your tasks, which are high priority, you can map those tasks directly onto the models that you're considering and get some gauge as to like, if I just deploy these models out of the box, do I expect them to perform well or not? And if not, then how do I fix them? And I think that's a very interesting direction for work.
Why aren't most agentic systems like continuing towards like real world impact of this work? Why are most systems not really ready for production? Like, are we one breakthrough array? And how might this work help move this forward?
I think it's a very top of mind question. And everyone has their own sort of take on it. I would say, coming from my background, I think on one hand, it's very case specific. I think there's lots of theories that have come out, like for example, customer support chatbots, like might have, if you look at some of the desiderata of these problems, like what are the aspects of like the customer service versus other things, like these might be like the most likely to go away. For example, with AI or with agents, because we're doing repetitive tasks. I think it's actually a pretty decent mental model. Like if you think about tasks which don't require novelty, these are the tasks which are very well fit towards machine learning. And again, deep learning is a specific instance of machine learning. Just give me the data on this job or this task. And if you just need my model to do what this data is doing, we have methods of doing that. That's what machine learning has been great at. The algorithms have remained largely the same for decades. We just now have a lot more compute. And so now we can get models to fit on a lot more data, which means we get models to memorize or like do lots more tasks. And that's why like scale is all you need is definitely like the way towards real world applicability for these models, because I can now absorb knowledge on God knows how many tasks. I think what I would question though is that even if you look at like customer service jobs, are these really rote memorization tasks? If there's at least an element of novelty, then we're now in a state where the models need to generalize. As we described before, they do generalize sometimes. They don't generalize reliably. If they're generalizing unpredictably, they're not generalizing reliably. So I would only expect, if my customer service job is 95% memorization and 5% novelty, what I would expect is that 95% of the time, it's the worst case, 95% of the time is reliable. And then that 5%, it's like a 50-50 on whether you're getting reliability or not. And then it's very interesting to kind of like, if you can detect that beforehand, if you can detect like this is the 5% where it's going to be unreliable, that could be useful for an agent builder. Because now I've seen even YC startups that are proposing this, like, what is their solution to reliability? A fallback, essentially. That if we can detect when the model is probably going to fail, then we fall back on rote code, like Zapier automations or things like that.
Which is really important. I know, Rob, you've written about that March of Nines, and we're getting closer, but we have to solve that last gap. So what you're proposing really is predicting where a model's going to fail to solve the problem.
Because if we look at, I guess, our current approaches, right, then there's the more academic question of like, are there better ways of going about it? We can talk a bit about that, about what's needed for generalization. The model needs to learn generalizable rules. And I think there's like some progress in that on like, how do we kind of curate and source the right data? Or like, are there neurosymbolic AI methods? But I would say, practically speaking, these are definitely far away from practically applying them. I would say practically today, we know generally how these models are trained. And because of that, we can detect like when we expect them to fail. And then in those cases, either we just go back to a human, just kind of abort, and like the human can kind of take over, or there might be even simple cases where you can fall back on some rule-based. And when I say rule-based, like rule-based AI is not very complicated. I mean, it can get complicated. It's essentially lots of if conditions. Like, I guess maybe the complicated stuff that's going on in this space is how do we build symbolic AI systems when there's thousands of rules and like maybe efficient ways of doing that. But if you were just write the code naively, it's just a bunch of if conditions. It's basically a decision tree at the end of the day. And so when I say falling back on code, you can even think of that as a neurosymbolic AI solution where we at least know the symbolic fallback because we know like what's the handwritten code that I would run if my agent fails. But there's likely a number of cases where you don't know what that fallback is. But there's still ROI. Like I've even seen people in the robotics case, in the robotics setting, which are like, look, we presuppose that these models are not going to be reliable. Maybe that's short term, that we can just scale up and cover all possible cases, and then generalization is not a problem. But then what I would argue against that is there's always another thing. There's always like, you can scale up on 1,000 tasks. There's always 1,001st task, which you haven't seen before. So it's very difficult for these models to be reliable. Symbolic AI is always reliable. It's very difficult for that to be general purpose because you have to code up the rules. You're very limited. And so academically or in research world, we're very far away from 100% reliable solution. So there's startups which are proposing being like, we are far away from a reliable solution. So maybe instead we assume these agents or robots, robot AI are unreliable. And so we're going to invest in like falling back in a human, things like that. And so I think those startups have decent staying power because like we're quite far away from not needing that at all. We're quite far away from reliable AI. Especially in very general settings like robotics.
I know you've spent time in both academia and industry, right? So just curious what kind of widely held beliefs in AI you think need interrogation. People have a lot of opinions about where we're at.
So I don't actually follow Twitter that often, because I mean, like it's a lot of opinions. It's a lot of back and forth. I think I've seen, I don't know how many different takes on whether we're in an AI bubble or not. Everyone has a take. I would say the one that I think about, especially in the context of this podcast, like inference-time tactics, is this idea that I think Noam Brown talks a bit about this. So he's one of like the lead people behind the O series of model, like the reasoning models from OpenAI. If we wanted, yes, it's more expensive to work with the reasoning models, but how much would we be willing to pay for a cure for cancer, for example? And in that sense, kind of justifying that like we might want to do crazy amount of test time compute if it somehow leads to a cure for cancer. And also in that same sentence, kind of being bullish on the idea that scaling test time compute could lead to a cure for cancer. I think the nuanced take on this is when we do like best of N strategies or any sort of test time compute, we are sampling at the end of the day from the model itself. And these models are generative models. They assign probability to a very high dimensional space that we can't really brute force. And so you could sample as much as you want, but if the solution, if the cure for cancer doesn't have non-zero probability in that space, then I'm not sure how far you're getting in terms of infinite sampling. Maybe you now sample also zero probability solutions, but there's going to be like an infinite number of garbage zero probability solutions. And so I think this presupposes like test time scaling leading to cure for cancer presupposes that the model has learned a good enough model of cancer, for example, or cure for cancers that maybe the 1,000th likely, like if you look at like, I don't know, if you rank by probability all potential solutions, that the 1,000th or the 10,000th, that it's somewhere there, right? It's not the 1 millionth or the 1 billionth. But if you just do the math on like how large these spaces are, if the model hasn't learned anything about cancer, it will be like extremely far away. And then in that sense, like you could be as well funded as you want, but you're going to still be stressing about finite capital. Like my friends at OpenAI, like these are the most well-funded places, but they feel like they're under a finite budget because they're doing something so expensive. And so you're still feeling that pain in that way of like the model doesn't understand cancer enough for me to, even if I throw the whole bank at test time compute, I still can't sample the candidate solution. And then you think about RL, right? Being like, oh, maybe instead of doing best event and all of that, I need to post-train and I'm going to use RL for that. Think about places like Poolside, et cetera, who are really investing in RL. I think it's well understood that not only is RL difficult to get learning signal out of, it's very much trial and error as well. And so I think Noah and Brown would even argue this, that the reason why RL works so well is because you're fine-tuning a pre-trained language model. And so why? Because RL gets signal by, I think there's methods of trying to get signal from negative rewards, but in the end, RL needs to see a solution in order for you to like, okay, I got a solution. I'm now going to fine tune the model so it only produces that solution. So again, it still fails in the same way that like scaling test time compute would be. If you never sample a solution as problem, you're always getting zero reward. And then I know there's negative reward RL methods, which just try to say like, okay, the 1,000 solutions don't work. Just never do those 1,000 solutions again. So discourage. But then you have another 1,000 solutions which don't work. In the end, this is all based upon the pre-trained model. So the model that was trained to do next token prediction, assigning some decent level of probability towards that solution. And we also know these pre-trained models are trained on the internet. And there's no cure for cancer on the internet. I think there are probably problems where, once again, like the model knows enough that fine-tuning helps you, but that means the model already knew the solution beforehand, and you're just filtering out the garbage. And like there's a good solution in the model, which means there's likely a good solution on the internet, which somewhat explains why these models have a hard time doing things that someone hasn't already solved before, because you're kind of filtering for that. I think that some of the problems they're being kind of pitched in terms of like, what will be the next breakthrough? How do we go beyond ChatGPT? And like do something fundamentally different, like get something fundamentally different since 2022, like cure for cancer, room temperature superconductor. I would never say that's not possible. Of course it's possible. I think there is healthy skepticism as to like whether we have the right approaches for getting there, when at the end of the day, it's all based upon whether a pre-trained model trained on next token prediction has assigned some probability to the cure for cancer.
Like you're in that camp where it's like cure for cancer may not be the next few years, right? But real world enterprise application and automation, we have solutions to solve that last mile problem where there are accuracy gaps.
Absolutely. So I think my prediction, what this basically means, going back to the 95%, 5% analogy, is that you take different tasks, like maybe the cure for cancer job, right? I don't know if that job exists, but like you're only good at this job if you cure cancer. Of course, that job doesn't exist. But in that job, we need 100% OD generalization, like come up completely new ideas that are not just new ideas, but good new ideas. Because you could try as much as you want on bad ideas. Who knows how far that will get you. Of course, like I don't think that some of these breakthroughs like penicillin, et cetera, a lot of them are like happenstance, right? They're not scientific method that we were very systematic about and we found that discovery. It was oftentimes just like, oh, it just happened. Like, we're seeing mold on like this like lab sample, for example. Why is there mold on that? And then like the scientists didn't plan it. It just happened. And so in that sense that, yeah, I guess random sampling is great. And so go for it. I don't know if cure for cancer is like a random sampling solution or a room temperature superconductor. We'll see. We'll throw the bank at it and see what happens. So there might be jobs like that where it's like 100% of the job is go well beyond the data distribution. And there might be jobs like, I don't know, customer support, things like that, where like 95% of the job is just follow what people have already done. Rubric, rules, lots of data on those rules. And so the models are pretty good at that. And you just need 5%. And I think the way to approach that is specialize in that way. Even in that 5%, is that 5% really come up with a cure for cancer? Or is that 5% just that GPT or OpenAI, there's God knows how many types of jobs in this world, and they just weren't able to specialize enough on that. Maybe enterprise, like a customer service company, has lots of enterprise data that they're keeping to themselves.
It's not on the internet.
Exactly, right? And so maybe that 5%, like 4% of it gets filled by just memorize our enterprise data, right? And just feed it to that. And now like 99% of the job is within the scope of these models. And then now when we have like 1%, now you have to do the human versus AI comparison, where I think they discuss this in self-driving cars as well. Like, do we really need self-driving cars to never have an accident when the alternative is humans who often have accidents? It's like the most dangerous activity you can do as like an everyday person, to drive a car. Maybe we just need to match up well or be slightly better than humans who are also unreliable in some of these settings, like unreliable at driving, unreliable here. And maybe humans aren't even like 99% performance. And so you get so far by just specializing in any of these domains. And we might not need that like ASI super intelligence sort of breakthrough, which I think there's lots of reasons to be skeptical about, given current techniques and just thinking through what we're doing in order to get good enough performance in these enterprise jobs. And I also don't think you necessarily need to intervene at the training stage. I think there's interesting ideas in context engineering world, for example, of ways we can be really cheap at inference time, but still feed the model with the missing data it has. So for example, you feed in a test example, like at inference time, what is inference, right? You're feeding in a test example, you get performance, you get outputs out of it. Maybe instead of investing all of our compute into output tokens, like the input tokens are very simple, and then we're just going to keep sampling. So output token after output token after output token until we somehow get the right output tokens. Maybe the way to kind of cut it down is to just, okay, this is a bit far away from what GPT is used to. I don't have enterprise. I have some enterprise data, actually. I don't need to retrain this model. I don't need to fine tune it. Maybe I just need to put it into the context. Just context engineer at this point. And maybe that's good enough. And I also know that Anthropic, OpenAI, they're very much pushing context engineering, which also means they're designing their models to be amenable to that enterprises can put their context into these approaches, which means it should work well. I think one can get very far in that direction.
Very exciting.
You had this Let It Wag benchmark that you launched, and curious if you could tell us a little bit about that and sort of what it measures and what you hope people can do with it.
The no zero shot paper where the Let It Wag benchmark was introduced, it was kind of showing that, like, as we said before, the representation of these test tasks in the training data really dictates the model's performance, especially when you're training from scratch, where it's completely knowledge based. And so what Let It Wag was showing was that let's take a bunch of different concepts or topics, like you might think of like dog, cat, for example. Like these are very well represented in the training database, so the model performs quite well on dog and cat. But what about like red-footed lemur, for example? You can quantifiably or even by your own expectation expect that like these are probably not very well represented in the training data. And these curves, like the log, we can talk about the log linear scaling about why that's problematic, but just the idea of that the model will perform poorly or worse on red-footed lemur than it would be on dog is fairly intuitive. And so by Let It Wag, we just wanted to get a number or get an eval that really tests that. So like, let's just curate red-footed lemur and all of the concepts that were not well represented in the training data and measure performance on this test example or test task. And I think there was a few interesting implications of that. One was that you saw some huge drop-offs. So there was, I think, a model that was trained on a very large database, so Common Pool. And Common Pool is like a uncurated curation, but uncurated sort of crawl of Common Crawl. And Common Crawl is just internet scraping. And it was a tiny model trained on that. And so I think in the AI research world, we know that like smaller models, surprising or unsurprisingly, depending on your perspective, tend to memorize. And so this is a small model trained on a huge data set. What we saw is that the model performed 60% on ImageNet, 20% on Let It Wag. So a 40% drop off here. What we saw in terms of the models that had less of a drop off, they were the models that were larger models curated on better data, for example. But all models consistently had drop offs. And then finally, I think in some work that was followed up by our lab, it was shown that like if we do some simple data balancing, for example, so instead of like if we know there's a long tail, that means like red-footed lemurs are like 5% of the training data and dogs are 50%. Maybe we don't need to train on dog constantly. Maybe we can balance and be like, well, sometimes we throw away maybe some of the dogs so that it's 5% dog, 5% lemur, or we keep all of the dogs, but we just continually include lemur in the training set or in the training batch. So when the model is updating its weights, it's updating its weights for dog and lemur, not constantly for dog, because dog is always present in the training set. It's going to completely forget about lemur. And these kinds of approaches do sort of equalize performance between ImageNet, which is lots of dogs and cats in common categories, as well as Let It Wag. The last thing I would say is benchmark construction. So I would say in both, the way we kind of did real world compositional generalization by just filtering real world evals for are they represented in the training data, and even for closed models, are they represented on the internet, basically, versus for Let It Wag of like curating these long tail concepts. There's God knows how many tasks you can consider, like even in LLM space. Like let's say you care about customer service application. You identify 400 sort of relevant things. You can rank them based on which of these are more represented versus not. And you can then curate some hard or difficult evals based upon that. Take like the subset, like the least frequent, for example, concepts in the customer service case, and then really stress test your model to see like, is it actually performing well on customer service? Or is there really, or the fact that we're getting 90% is because on 300 of the 400 concepts, they're really well represented. And so we're doing really well on them. We're doing really poorly on the last 100. And so it's kind of like, how do you assess reliability? It's quite simple. You do stratified evaluations. You don't pool and just get an average performance across all your data because all your data is very imbalanced. You then just split your data in certain ways and then find out, okay, there's a failure mode here. There's a failure mode there.
We'll definitely appreciate the deep dive. We've gotten really tactical on this one. Very helpful for our listeners, but also some bold predictions about where we're at, where we're going. Maybe not a cure for cancer in the next 2 years, but definitely a lot more performance gains to come, especially with orchestrating systems and some of the tactics that you mentioned. But with that, thank you for joining us today. Everyone, please like and subscribe. We're going to include links in the show notes. Thanks for joining Inference Time Tactics.
Of course, appreciate it. Thanks for having me.